Hi, my name is Mohammad Faveed Arif. Today I will present our work called SYSLITE. It is a joint work with my colleagues Daniel Araz, Mirzwa Shabir, Andrew Reynolds, and advisors Umar Chaudhary and Chezre Ali. All the authors of this work are from the Department of Computer Science in the University of Iowa. Before we move on, I would like to introduce the problem of PLTL formula synthesis, in which a PLTL formula synthesis takes two inputs. The first one is a set of atomic propositions, and the second is a training or a sample data. A training or sample data set consists of two disjoint sets, which contains the green one are the positive set of traces, and the red one with the dotted circle are the negative traces. And a trace is a sequence of states, and each element of this set is a finite length trace. So given these two inputs to PLTL formula synthesizer, it generates a PLTL formula such that all the positive traces were satisfied by this formula and all the negative traces were falsified by this formula. If we look at carefully, then this kind of a synthesis problem is a special case of language learning from the informant problem, in which we are trying to learn past time linear temporal logic from finite length traces of a given example. This problem has a list of applications ranging from security policy mining from system logs, software and system debugging, security policy authoring, and attack signature and root cause generation, and many more. In particular, in this paper, we are focusing on attack signature and root cause generation. Our target application is to monitor attacks on 4G LTE protocol, in which a adversary sending an unordered sequence of packets on the air can cause several attacks to happen. One of them is a num attack, which can make a system to halt. Other attacks are AKA bypass, which result in eavesdropping, and many more. If we look at this problem, then one thing is common. All these attacks are due to a buggy 4G LTE protocol state machine, in which a system implementation is unable to handle out of order protocol packets which were sent by an adversary to take an advantage and achieve a desirable goal. So in our project, what we envision is a cellular device centric warning system in which we have a monitor that monitor the packets. There'll be a radio modem along with a SIM which connects to a provider, service provider, and the radio signals were being broadcasted and received from the provider base station. And then modem, then monitored in real time the packets from the modem. Then it checks a signature in the attack signature DB. And in case if there is a violation, then it alarms the user about being detecting an attack. Problem to consider here is that how to specify these attack signature that encapsulate the representation of an attack. If we do it through by means of a manual writing, then it could be error prone or cumbersome to write. So here we can use PLTL formula synthesis to generate us these signatures, where we make positive examples or consider positive example as our benign execution phases and attack phases as negative examples, which tend help us to learn an attack signature in a representation of a PLTL formula, which then being used to detect an attack. In this paper, we concentrate on PLTL formula synthesis part. Before I present, let's enumerate over our contribution, where the first one is to not only present a list of solutions, but also evaluate the bottlenecks of prior work. Along with this, we proposed a solution where we reduce the problem of PLTL synthesis to a bit vector function synthesis to achieve the required scalability, which we'll talk about later. And our system, which we propose, SYSLITE, along with 2 case studies, have gained a speed up of 28x to 60x over the baseline. So I've already gone over motivation and contribution. Now I'll quickly describe the background and the related work. So one of the background is PLTL pastime LTL, which is an extension to propositional logic with pastime LTL operators, which contains both the unary operator, temporal operators, historically once, yesterday, and a binary operator called since. Interestingly, all other operators can be defined in terms of yesterday and since. And these temporal operators, their semantics were defined in terms of finite traces, which are sequence of states, and each state is a mapping to maps a propositional variable to a Boolean value. And this green arrow says, for example, this is a current state, and here it is saying yesterday A. So in order for a yesterday A hold to be held in a current state, A should have been held in the previous state. Likewise, for a binary operator A since B to be hold or a true at a current state, it boils down to being B was being held sometime in the past, and from there onward A was true including the current state. To the second part of our background is syntax guided synthesis or syntax guided synthesizer, which takes 2 inputs. One is the syntactic restriction, which was given in the form of a context-free grammar. Second is the semantic restriction, which either contains formulas or examples. And given these 2 inputs, the synthesize function or the synthesize function conforms to the context-free grammar. At the same time, it satisfies the semantic constraints. So going back again to our proposed problem, where we would like to detect cellular network attacks. The attack signature synthesis problem we would like to solve in this work. And for attack signature, so one can ask that what could be possible representation of attack signature representation. So it could be a DFA, or as we were proposing in this work, to represent as a PLTL formula. So if it could be a DFA, let's consider a real-time attack, aka bypass, which caused an eavesdropping. We learned a DFA from using an RPNI algorithm implementation in LearnLib, and you could see the structure of this. At the same time, SYSLITE let us learn a very concise, succinct, and a small signature. And it's not only we could able to learn this, a succinct representation of a signature, but it also yield other benefits. Namely, the learned signatures were amenable to an efficient space monitoring. as well as they yield much higher precision and recall. And as I was describing before, that these signatures are understandable or human interpretable. And the only downside, which through our evaluation we reached, is that it is less scalable than RPM. So since we have already motivated that PLTL synthesis has an interesting application, especially in our context, we will quickly go over some prior work where LTL synthesis problem was being solved 2 years ago in FMCAD. What they did was that for linear temporal logic formulas, they reduced it to the problem of Boolean satisfiability problem, where a monolithic formula contains two conjuncts, where the first conjunct specify the syntactic restrictions of an LTL formula of a certain depth as an EST. And the second part of the conjunct define the semantic constraints or restrict the formula for defined to be consistent with the given sample or a training data set. And both, once this formula is being provided to an off-the-shelf solver, from the model an LTL formula can be get extracted. But unfortunately, this work we cannot use right away because it was only using synthesis over future only temporal operators as well as considering infinite execution phases. And unfortunately, it was not scalable enough to be used as our application. So I have to quickly go on over motivation and contribution and background and related work. Now I'll go over our proposed system. It's called SYSLITE, but before that, presenting the design of SYSLITE, I'll present a list of unsuccessful attempts while solving these problems. So first, what we tried is we tried to adopt this set-based method to learn pastime LTL over finite traces. But what we found out is that the syntactic restrictions are not sufficient enough to rule out redundant formulas, as well as there's not sufficient support for symmetry breaking, so that we can found diverse formulas. And encoding semantic constraints for each step of the trace is cause a scalability issue, which we'll see later on. Then there was an extension to this work where the shapes were pre-computed, but it's not only cause pre-computation, but also it's not a memory because it has a high memory requirement. And for us, if we would like to have a monitor within a cellular device, then we would like to consume the least amount of memory, as well as it suffers the same problem of being with the symmetry breaking as well as point-wise semantic checking of the constraints. So the next two methods are the ones which we proposed. One was encoding the syntax as a ADT, algebraic data type, and then encode the point-wise semantics. And similarly, in one we used SYGUS, context-free grammar, to represent. But unfortunately, these two carry over the same scalability issues as the prior work. And what we learned is that symmetry breaking is essential, so that if we can discard unnecessary solutions, then they help us to become scalable. Second is that native theories provide specific optimizations, which are very essential. And lastly is that point-wise semantics checking where we are checking at each step for a trace is really crucial for scalability. So in using these insights, we propose our encoding where we reduce the problem of syntax-guided PLTL synthesis as a bit vector function synthesis, and in which for every variable in a trace yield to a bit vector of itself. For example, if trace contains 5 variables, then there will be 5 variables. And we defined PLTL temporal operators in terms of bit vectors. This way, we could able to use bit vector which is natively supported by the scikit solver. As well as using bit vectors, we can consider the whole trace for checking the consistency with the trace sample set. These insights help us to propose our solution, SYSLITE, which is a wrapper around CVC4 scikit solver CVC4 SY, in which PLTL syntax is given as a context-free grammar, and then consistency with the sample is given as semantic constraints, and once its scikit is being queried, it returns a PLTL format. So we have described motivation, contribution, background, and our system. Now we'll go over the evaluation. So we solved the problem of scalability. But at the same time, in order to solve the scalability, we would like to be ensured that the effectiveness of the solution or the correctness or accurateness of the solution is not being compromised. So we conducted 2 tests, or these are our research hypothesis questions, that how scalable, at the same time how effective the SYSLITE is. So in order to evaluate the effectiveness, we considered formulas from the literature, and for scalability we ran our proposed application, motivated application. For baseline, we use neither and get one set-based algorithm. For timeout, it's 1 hour. For memory, it's 15 GB. And we considered variable size of training dataset, and in which 80% are for training and 20%. In the case study 1, where we were trying to evaluate the effectiveness of the solutions which were being computed by SYSLITE, we collected 8 different safety formulas from the literature, and we used these formulas as an oracle along with a pseudo-random generator to generate traces for our SYSLITE. So these traces contains a random noise, and then we generate first 5 candidate traces using SYSLITE as well as the baseline. And what we did was we tried to check the equivalence, whether SYSLITE can, and the base solution can learn back these formulas or distill the noise and learn back these formulas. And in case if they are not logically equivalent, at least what was the precision recall measure on this. So in this table, we could see that SYSLITE was able to learn back 7 formulas out of 8, where at the same time baseline was unable to learn half of the formula. Recall that we were computing first 5 formulas. Then we could see that for equivalence checking, the 31 instances were equivalent to the seed formula as compared to the baseline. And on a precision and a recall, could see that the 100% precision and 300% recall was much more better than the baseline. But at the same time, one could ask that could it be the case that the failure to generate an equivalent formula could be attributed to the timeout? So we make another experiment where in this graph on an x-axis, the training data set size is there. On y-axis, we have the training time. Of course, it is on the log scale. The red line is attributed to the timeout, and these are the formulas which we ran. And here we learned that we could able to achieve a 6x improvement over the baseline. And in the table, we could see that SYSLITE only timed out lesser, much lesser than the baseline. So here only 3 instances out of 40 and for the others. And going back to our case study on cellular network, we would like to see that how scalable SYSLITE is to let us generate a signature. We consider 10 real-world attacks where we collected benign traces from Mobile Insight, where from all over the world researchers submit traces. And for our negative or attack traces, we build a test bed in which we use software-defined radio network and executed and implemented the attacks to generate, to collect the attack traces. And here, the same parameters where on the x-axis we have the training data size, and on the y-axis we have in log scale the training time. Could see that SYSLITE performed 28x over, has the 28x improvement. And here the SYSLITE was able to generate attack signature for all the considered attacks, where a baseline was miss out or to generate a trace for one attack. And both have the 100% precision and recall for the tested. And of course, another fact that SYSLITE timed out for a very few number of instances as compared to the baseline. So as a summary, what we did is that we explored several solutions. We identified the bottlenecks and the shortcomings, which we addressed by solving this problem through smart encoding, which was being proposed as a bit vector synthesis for PLTL. To solve the PLTL synthesis problem, we developed a scalable and efficient approach for PLTL formula synthesis. We implemented it in our tool called SYSLITE, and SYSLITE can synthesize correct and diverse formula while exhibiting a much higher speed up over the baseline. So it's an open source tool which is available at the link along with experiments, data, and encoding.